Hello. So in this video, we'll be seeing the min stack problem from lead code, which is LC155. Let's start. So here, what the question says, firstly is design a stack that supports push, pop, top, and retrieving the minimum element in constant time. We need to implement the min stack class. Min stack will initialize the stack object. The push function will push the element value onto the stack. Pop will remove the element which is present on top of the stack. Top will retrieve the top, and getmin will retrieve the minimum element of the stack. All right. Uh, so here is a special note which you can see, which is you must implement a solution with O of one time complexity for each function. So we need to have constant time complexity for each function in this min stack class, right? Let's see the test case which is given here. So the input of the test case is firstly min stack. So that will initialize our stack. Then we have a push, we'll push -2. Again have a push, which will push 0. And again we have a push which will push -3. Then we have a get min. So what is the minimum element? So it is -3. So we need to return -3. As you can see, it has returned -3 here. Then we do a pop operation. So we'll pop -3 because we know that stack follows LIFO. So -3 will get popped out, and this is here null. Then we try to retrieve the top. So what is the top element? So since -3 got popped out, now we have 0 as the minimum element. Sorry, 0 as the top element. So it will return 0 here. And then again we do a get min. So out of -2 and 0, which is the minimum element, it is -2. So we are returning -2 here. Right, so this is the explanation of the same thing. We can see min stack is equal to new min stack. So it has initialized a stack class, and then we have a min stack push -2, a min stack push 0, min stack push -3, get min, pop, top, get min, right? So these are the constraints. The value should be -2 raised to 31 to 2 raised to 31 minus 1, and all of these method operations will always be called on non-empty stacks, right? So the stack cannot be empty, and at most 3 into 10 raised to the power 4 calls will be made to push, pop, top, and get min, right? So that was the problem for us. Now let us start seeing how we can actually think about a solution for this, right? So we'll just shift to the notepad. Yeah, so we have shifted to notepad for a better understanding. So what do we need to do in this problem? Firstly, we need to implement push, then we need to implement pop, we need to implement top and get min. I hope you are well versed with the fundamentals of stack for this problem. Other than that, it will get a little difficult to understand. Yeah, so these are the functions. I hope everyone knows how they work, and how we actually make use of them in our normal problems. Alright, so the main constraint of this problem is that we need to implement this in constant time. So for push, pop, and top, we don't have any issues in implementing them in constant time, as anyways they'll work in constant time. But the problem arises with the get min function, right? So what is our intuition? So suppose we have a stack 37285. Now we can see that the current min element is 2, right? From the stack, the minimum element is 2. But what our intuition says is, anyone asks us for a get min, anyone calls get min, we'll just traverse the array and return the minimum element, which is here -2 for them. But the problem arises that the traversal will take O of n time complexity, right? But the problem is asking for O of 1. So what is our second thought here? Our second thought here is to store the minimum element separately. What we can do is we can create the stack and we can store the minimum element separately. So here minimum is -2. We have stored it in uh, a different variable. So here we have a variable minimum and we have stored 2 in it, right? And now as soon as someone calls getmin, it basically converts into the code block of return minimum, right? We are just simply returning the minimum variable here. So this will take O of 1, but this has a small issue. Suppose that the stack was not 37285, considering this is the stack top. So suppose that the stack was this 23785. So if the stack was 23785 and someone would call the pop operation, right? Someone would perform pop on this, 2 would get removed, of course. Now our hoax of this variable burst with that, right? So since 2 is now removed, we again need to traverse the array to get the minimum element, and that will again convert into O of n time complexity. So we cannot do this too. So how do we actually tackle it? Now let's move to the actual solution. So as we noticed, difficulty is occurring when the minimum element is removed. We were able to store it here perfectly fine, but as soon as it got removed, that is where the problem arises. So we need to think about history. Basically, we need something which can create a history for all of the operations and all of the elements and all of the values. So we need to ask at some x point in time, what is the minimum? That should be our question, right? So now let's dry run something, and with that we'll be able to understand what we exactly need to do. So suppose we push 5. Okay. Now I ask you, what is the minimum element here? Of course, there is no element already present in the stack, so the stack is already empty. So the first element, which is 5, should of course be the minimum element, right? So the min here becomes 5. Now suppose we push 8. We again ask, what is the minimum element here? Remember this question. So we again ask, what is the minimum element? It is still 5, because if you compare 8 and 5, of course the minimum is 5. Now suppose we are pushing 2. We again ask, what is the minimum? So here the minimum will change. We are comparing 5 with 2, right? So the minimum element is 2 here. And now we are pushing 7. So now what is the minimum element? It will still remain 2, because 2 is smaller than 7, right? So basically this becomes our stack with values 5, 8, 2 and 7, and minimum till here. We'll store minimum till here at every point. So for 5 the minimum was 5, then we pushed 8, the minimum still remains 5, then we pushed 2, the minimum becomes 2, and then we pushed 7, the minimum still remains 2, right? So this is our minimum at any point in any given point in time. Now suppose we pop, right? So since 7 was pushed the last, so we'll pop it, so 7 will get removed, right? Suppose we remove 7, what will happen? At any point we still have the minimum element, so the history is getting saved. If this part even gets removed, we have 2 with the history of 2, which is minimum till this point, so there won't occur any issue, right? Now the problem is, how do we store both the values? So instead of directly pushing 5 onto the stack, we can store it as a pair. It is a key value pair, so which is 5, 5. This is the first part, which is the current element, and this is the second part, which becomes the minimum element. So our stack will become something like this, right? So suppose this is the top, so we first pushed 5. 5 goes at the bottom, and 5 is also the minimum element. Now we push 8 and we compare, right? So between 8 and 5, which is smaller? So we have 5. Then we push 2, we compare between you can say 8 or 2 or 5 or 2, right? Still the smallest element remains 2, and then we compare 7 with 2, it still remains 2. So at the top we have 7 comma 2, so 7 is our top and 2 is our minimum element. First number is the actual value and second number becomes the minimum until that point. So the formula while pushing becomes new min is equal to min of value comma current min. Okay, so what does this mean? So new minimum is equal to the minimum of, so we need to compare two values, which is first one the value being appended, the value being pushed, and the second one is the current minimum. So the current minimum is 2. So we compare 7 and 2. So 2 is the minimum. So that is why we push 2 as the new minimum. Right, so I suppose it was clear until here. We'll just see how we implement all of this in code. So pop remains as usual, no changes. For returning top, we'll do top dot first. So as we saw, we are storing it as a key value pair. So since we are storing it as a pair, we need to return the first part of that pair, right? I'll just show it here. So here 5 5 or 7 2. So if we need to return the top, so the top element becomes 7, and if we need to return the get min, so that becomes 2. So top dot first, and for get min we do top dot second. So now we'll just implement this in code on LC. So I'll just quickly code this up, right? So first we create a stack of int comma int, right? We'll name it st. So this becomes our stack. We do not need to do anything in this min stack, so this is just an initializer. constructor class, and then we'll push the element. So while pushing, we need to take care of two things. Firstly, what if the stack is empty? So if the stack is empty, we just push the stack key value pair, right? So we are just pushing the first element which we need to push and not actually running any conditions here because the stack is already empty. So there is nothing to compare. So if st.empty, we need to just push the element, right? So this becomes our first thing, and else if there is something already present, so we need to fetch the current minimum. So current min will come from st.top. Second, right? So as we saw, it will come from the second part of the key value pair, and then we'll just push it. By comparing the min of value from a current min, which we just fetched. Right, so that becomes our push. And for popping, we just need to do st.pop as usual. And to return top, we need to do return st.top dot first. Right, and for getmin, as we saw, we need to return the second part of the topmost element since it is a pair. So yeah, so that becomes our code. We'll just run it. Right. I forgot to mention it as a pair of int comment. Yeah, that works. We'll just submit the code. Alright, so it is passing all of the test cases. So that was the implementation of LC155. I'll mention the code and also the link to the problem in the description so you all can go and solve it yourself. Right? Thank you.